This is the last lecture in Chapter 7, and it is all about orbitals, which you've probably heard about. That would be like s orbital, p orbital, d and f orbitals. And it's also about quantum numbers, which you may not, unless you took AP Chem. Not quantum mechanics, quantum numbers. They're rather bizarre, and so when you get to the latter section on quantum numbers, you may need to listen more than once and make sure that you're a little bit fresh. They're very abstract concept. So just as a quick review, I mentioned in a previous lecture there were several scientists that contributed discoveries to our current model of the atom, which is the quantum mechanical model, and one of them was Einstein. Einstein did experiments with what we call the photoelectric effect. That's basically shining light on different types of metals and observing the electrons being ejected. And what he found from the work that he did is that light has energy that's delivered in packets. Those packets now are called photons of light, or sometimes quanta of light. And a photon of light has an energy equal to h, we call this little crooked v, nu, okay, where h is Planck's constant, which you've hopefully worked with a bit now when you're doing your calculations with light, 6.626 times 10 to the minus 34 joules per second, and this is just the frequency of light. And so that led to Einstein proposing that light, it was well known it had behaviors of wave behaviors, kind of wave diffractions and things, but now Einstein also proposed that light can behave as a particle. And so, again, as a reminder, de Broglie then built on Einstein's work and said, well, light has a dual nature. It can behave as a particle or a wave. And so de Broglie proposed that matter, things that contain mass and occupy volume, like you and me, or an atom, could also behave as a wave. And so he set about to do some research and found some pretty good evidence to support that theory. And the equation he came up with, which is supported by data, is that the wavelength of some type of particle of matter is inversely proportional to the mass of that particle. Okay? So that as mass goes up, as it gets to be a larger and larger object, its wavelength associated with it would go down. So de Broglie's argument is things with very large mass, like you and me, or a car, or a house, have such small wavelengths that we really don't have experiments to monitor the behavior of the wave. However, if you have very small particles, like an electron, they would be associated with wavelengths that are quite a bit larger, and it turns out large enough for us to observe evidence of wave diffraction behavior. So de Broglie's equation describing the wave behavior of matter is in fact supported today by theory. And one scientist that we haven't talked about yet, but you might be familiar with, you probably have heard of Heisenberg's uncertainty principle. And basically, after years and years and years and years and years and years of trying to study the electron and failing to learn much information about it, Heisenberg proposed his uncertainty principle, which basically says that you cannot know the position of an electron and its momentum. Just think of it, it's not really speed, but I want you to think of it as speed now. You can't know those two pieces of information at the same time with certainty. If you get a good handle on the position or location of an electron, you have lost information about its speed and momentum. And that's simply, it's very basically, the only way we have really to observe something is to shine some type of electromagnetic radiation on it so that we can effectively see, not see with our naked eye, but observe. But the very act of shining light on an electron changes its momentum, so we lose information. And so Heisenberg theorized that there's no way around the uncertainty principle, that by its very nature we can get information about the position or the momentum of an electron, but not both. So then along comes my hero, Schrödinger, and Schrödinger pretty much put everyone's idea together. He put the concept of matter, de Broglie's matter can act as a wave. He took Heisenberg's uncertainty principle, and he made these fantastical mathematical equations describing the wave behavior of electrons in an atom. So if you look up Schrödinger's equation, it's monstrous. He was a really good mathematician. And when he solved these mathematical equations, he got a bunch of solutions. If you've been in calculus, you realize you can get multiple solutions to one equation. And each solution gave him an area of space, okay, described by these dot density maps here. And so he called these areas of space orbitals and said that they were an area of space where an electron is most likely to be found. Okay? So an orbital is an area of space where an electron is most likely to be found. Still to this day, Schrödinger's model of the atom is our accepted model of the atom, and we call it the quantum mechanical model of the atom, or kind of a nickname, the electron cloud model. And that's because if you draw out one of Schrödinger's orbitals in what we call a dot density map, it looks kind of like an electron cloud. And really what it is this whole area represents the region where we can probably find an electron. I think it's like 95%, it might be 99% probability, according to Schrödinger's math. But where these orbitals are the densest or darkest means that there's a higher probability that the electron will be in that space. Okay? And when there's no density, that means there's zero probability that you will find the electron there. And so that's kind of how to interpret. This is an s orbital. S orbitals are spherical in shape. Some of Schrödinger's math equation. Whoops, let me go over here. You do have an s orbitals for different energy levels. Energy level 1, energy level 2, energy level. And that's kind of building on Bohr's model, which said that electrons have to exist in certain energy levels. And so if you remember, the energy level closest to the nucleus was n equals 1, and then n equals 2, and n equals 3. That's what these numbers designate in 1s, 2s, and 3s, the different energy levels. So each energy level has an s orbital, but the s orbital becomes larger in diameter at higher energy levels. All right, then another solution to Schrödinger's wave equation are p orbitals, which are described by most people as dumbbell shape. And now I want you to think about x, y, and z axis. The z axis is coming straight out at you. I'm just not a very good artist. If you have a spherical shape, there's only one way to orient it. Think of a basketball. You can rotate it in as many different directions as you want, but it's still going to look the same when you're done. So an s orbital has only one orientation in space. Okay, whereas a p orbital can be located along the x-axis, the y-axis, or the z-axis. So a p orbital has 3 orientations in space. If you get that to sink in now, that'll help you understand quantum numbers later on. All right, onward to... So the d orbitals just get funky, and you're not normally asked to describe them because they get rather odd. There are 5 orientations in space of a d orbital, but one of them doesn't even look the same as the others. Most people describe the 4 out of the 5 d orbitals as clover shaped. Okay, I'm not going to focus much on the d orbitals, but do remember that there are 5 of them. That'll help you with quantum numbers also. And f orbitals are usually not even drawn. I suppose they are too abstract for us to put onto paper. So I'm getting ready to transition into quantum numbers. Quantum numbers will describe the orbitals in more detail. But before I do that, I want you to visualize these orbitals that I've just briefly described. So think of a Bohr model. Here's the nucleus, all right? And then it has energy levels around the nucleus where the electrons reside. Okay? And so we have, if that's the nucleus, then we have n equals 1, n equals 2, etc. If you haven't already realized this, each energy level represents a period on the periodic table. So if an electron is in n equals 1 energy level, that means you will find it on period 1 of the periodic table. This all gets to be a pretty cool big puzzle that all fits together. So an electron in energy level 1 can have, according to the mathematical equations, can exist only in an s orbital. Electrons found on energy level 2 can exist in either an s orbital or a p orbital. Electrons in energy level 3 can exist in either an s, a p, or a d orbital. Don't get concerned about the mix-up of the 3 and 4 here. It's funky, but I'll explain it later. And so you may notice that the number of sublevels in an energy level. What do I mean by sublevels? I mean S, P, D, and F. So the number of sublevels within an energy level equals the energy level itself. So if the energy level is 1, that means there's one sublevel, and it's S. If the energy level is 2, that means there are 2 sublevels, and it's S and P, etc. Kind of setting you up to hopefully help a bit when we get to the weird quantum numbers. So I'm going to go ahead and start telling you about quantum numbers. Don't get too frustrated at how odd it is. I would recommend that you're settled in and paying attention and perhaps jotting some notes before you start it, and you may need to listen to it a couple of times. All right, the first thing to understand is that there are 4 quantum numbers that describe the location of every electron in an atom. There are 4 quantum numbers that describe the location of an electron in an atom. So you can point to any electron in an atom and assign it 4 different quantum numbers, and every single electron in that atom will have its own unique set of 4 quantum numbers. And so it's basically a little bit of statistics there. Scientists just realized they needed 4 different numbers to describe the energy, the location, the orientation of an electron in an atom. So the first quantum number is just designated as little n. We've talked about that. And that's simply the energy level of an electron. As I mentioned before, n also corresponds with the period number on the periodic table. So if you're looking at the periodic table and you have period number 1 with hydrogen and helium, and you have period number 2 with there's not a thing there, with quite a few atoms. So n equals 1 corresponds with the elements on the first period. N equals 2 corresponds with all the elements and their electrons on the second period. So n can have values of integers corresponding to all of the energy levels on the periodic table, and there happen to be 7 of them. The second quantum number, and this is where it gets a little odd, is designated as L. It's usually kind of like a lowercase cursive L. L describes the shape of the orbital, and basically L is referring to S, P, D, and F, those sublevels we talked about within each energy level. Okay, that's what L is referring to. Its formal name is angular momentum quantum number, whereas N was the primary energy quantum number. So the values of L, it starts at 0 and then goes one integer at a time, 1, 2. The highest value that L can have is N minus 1. So pay attention for a minute so I explain what the heck that means. So if N equals 1, let's say the first energy level, L can have values, they always start at 0, of 0 up to N minus 1. Well, if N is 1, 1 minus 1 equals 0, so that means if N is 1, the only value L can have is 0. Kind of boring. So let's do what happens if N equals 2. If N equals 2, if the primary energy level is 2, the values that L can have, again, it always starts at 0, so it can have a value of 0, and it goes up in integers to a value of N minus 1. So if N is 2, this is 2 minus 1, or 1. So L can go as high as a value of 1 if N is 2. So for energy level 2, L, which is describing the sublevels or the shapes, can have values of 0 and 1. So if L has a value of 0, they're talking about an s orbital. If L has a value of 1, they're talking about a p orbital. If L has a value of 2, they're talking about a d orbital, and I don't know why I left this out. If L is 3, we are talking about an f orbital, which we can't draw. So it's just garbage. Okay. So you might ask, why do they have to give these numbers? Or why can't they just say S, P, D, and F? My point exactly. So anyway, onward to the third quantum. All right, third quantum number is called the magnetic quantum number. It is M sub L. And yes, this sub L is in reference to the L, the angular momentum quantum number we just went over. And M sub L is the orientation of an orbital. I hope you remember a few slides back, I was telling you that an s orbital only has one orientation in space, because you can rotate it, it still looks the same, whereas a p orbital can lie along the x, y, or z axis, so it has three orientations. Okay, that's what M sub L talks about, the number of orientation. And so M sub L varies from values of minus L to plus L. So you can't figure out M sub L until you know L. So let's see, if L has a value of 2, and what did we say that was in the last page? We said that was a d orbital if L is 2. So if we're talking, about d orbitals and L equals 2, the values that M sub L could have, it varies from minus L to plus 2, so it's varying from minus 2. It rises in integer values and goes through 0, so it can go from minus 2, minus 1, 0, plus 1, and plus 2. So those would be the values of M sub L if L were to be 2, a d orbital. You might remember from a couple slides ago that I said d orbitals can have, there are 5 of them, that can have 5 orientations of space. Those 5 d orbitals are designated with an ML value of minus 2, minus 1, 0, plus 1, and plus 2. I know it's very bizarre at this point. Hang on as much as you can, and then if you need to, go over it again. The fourth and last quantum number, yay, is called M sub s. And that little s is referring to the spin. This is an easy quantum number. Basically, it can only have 2 values. An electron can either be spinning clockwise or counterclockwise. And so we assign an ms value of plus 1/2 if it's spinning clockwise, or minus 1/2 if it's spinning counterclockwise. The way we represent that on pen and paper is with an arrow. An up arrow implies, just by convention, it's a clockwise spin electron. We give it a designation quantum number ms of plus 1/2. If you see a down arrow, that represents an electron that is spinning counterclockwise and is given an ms value number of minus 1/2. Let's look at a quick summary, and then I'll do a couple questions, and then I am going to have a worksheet, which you're definitely going to want to go through, posted in the folder on D2L called In-Class Problem Solving. Here are the 4 quantum numbers that are used to describe each and every electron in an atom. And each and every electron in a single atom has a unique set of 4 quantum numbers. They're each different from one another within one atom. So we have the principal quantum number, n, which tells the energy level. We have the angular momentum quantum number, L, which tells us the shape of the orbital, S, P, D, or F. We have the magnetic quantum number, which is m sub L, and tells us how many orientations in space that orbital can assume. And finally, the spin quantum number, m sub s, which has only 2 different values, plus 1/2 or minus 1/2. If you are a visual learner, this is what the orbitals look like. There's only one orientation of an s orbital. P orbitals are dumbbell shaped. There are 3 different orientations of them. And d orbitals, there are 5 different d orbitals. Alright, so kind of remember that. S has 1 orbital, P has the S, we'll call it S sublevel, has 1 orbital. The P sublevel has 3 orbitals. The D sublevel has 5 orbitals. So kind of remember that 1, 3, 5. Jot it down even. All right, another visual. This one can be overwhelming, but I am going to walk you through it. This is combining information about all 4 quantum numbers. So energy level 1, n equals 1, okay? We can only have s orbitals, okay? So if you remember, let's see, if you remember, then if n equals 1, L has to equal 0, which means m sub L, there should be a little sub L there, also must equal 0. So you only have an s orbital in n equals 1 energy level. So as we get more into electron configuration, you'll see that the elements in period 1 are just hydrogen and helium, and you'll notice as we progress that their electrons are only in s orbitals. Alright, moving on to n equals 2, the second energy level in the periodic table. If n equals 2, L can still have a value of 0, so there are still s orbitals in the second energy level, but L can also now have a value of 1. If L has a value of 1, that means you're talking about the p sublevel. We know that there are 3 p orbitals in a p sublevel, okay, and then those are the only values of L that the second energy level can have, is L equals 0 and L equal 1, or s orbitals and p orbitals. I'm not going to go in that much detail because it kind of balloons in complexity, but energy level 3 can have s orbitals and p orbitals and d orbitals. Do you remember the correlation I gave you before where I said there are as many types of orbitals in each energy level as the energy level itself? So for energy level 1, there's 1 sublevel, and that's s. For energy level 2, there are 2 sublevels. See, the 1 matches the 1, the 2 matches the 2. And the 2 sublevels in energy level 2 are S and P. For energy level 3, there are 3 sublevels, and those 3 sublevels are S, P, and D. And of course, 4th energy level has S, P, D, and F. So that's probably another little correlation that is worthwhile jotting down. And a final visual. If you don't like all those pictures, this is more kind of a logical representation. and it's ordered in a way where energy starts low at the bottom and goes up, which is kind of more conventional. And so energy level 1, the values that L can have are only 0, which means energy level 1 only has the S sublevel. Okay, and we call that 1s. I'm getting you ready for electron configuration. Energy level 2, n equals 2. There are 2 possible L values. There's L equals 0, which is referring to an S sublevel, and there's L equals 1, which is referring to a P sublevel. Of course, all S sublevels only have 1 orbital in S, and P sublevels have 3 orbitals. So the second energy level has S and P sublevels. We call them 2S and 2P. Energy level 3, if you go all through that rationale again, and I would recommend that you put me on pause and try to understand this pictorial. So energy level 3, there are 3 values that L can take, 0, 1, and 2, which means energy level 3 has 3 sublevels, S, P, and D. And within each of these sublevels, there are different orientations of the orbitals. S only has 1 orientation, so we only have 1 S orbital. P has 3 orientations in space, so there are 3 P orbitals. D has 5 orbitals. Okay, so the third energy level has S, P, and D sublevels. Alrighty, so let me give you an idea of the type. This is all conceptual. There aren't math in this lecture. Let me give you an idea of the type of questions I might ask you about quantum numbers. I might give you a pictorial like this and say, which of these 5 orbitals could have quantum numbers of n equals 3, L equals 2, and m sub L of 1? And let me walk you through how you would figure that out. N is always easiest to tackle. N is the primary energy level. How is the primary energy level shown? It's shown simply with a number. Remember, N can equal 1, 2, 3. Well, they're telling you here that N is 3. So what can we eliminate? Well, here, 2p orbital, this 2 means its second energy level. We can cross that one out. So anything that doesn't have a 3, because that number represents N, the primary energy level, can get crossed out. So now let's talk about the information we can get from L equals 2. You might remember L tells us about the shape of an orbital, and you just kind of have to memorize these. If L equals 0, you're talking about an S orbital. If L equals 1, you're talking about a p orbital. And if L equals 2, you're talking about a d orbital. Guess what? We've just solved our problem. If L equals 2, you're talking about a d orbital. There's only 1 d orbital among these choices. And so these quantum numbers, n equals 3, L equals 2, are referring to a d orbital, and that is your answer. So that's a level of understanding you need to have to be successful on the quiz and on the upcoming tests to do with quantum numbers. All right, so here's one more question you can practice, and what you probably want to do is read the question, understand it, put this lecture on pause, and see if you can answer it yourself. The first question is to look at these designations for the 5 different orbitals drawn here, and first try to assign each of these designations, 3d, 2p, to which orbital they belong. You should be able to know that based on their relative sizes and shapes. And once you do that, I also want you to assign quantum numbers. You will only be able to assign 2 quantum numbers to each of these orbitals because I haven't given you information about orientation in space or spin of the electron. But you should be able to assign two quantum numbers, the n value and the L value for each of these orbitals. And then I want you to answer the question, which of these 5 orbitals could possibly have these 3 quantum numbers? And I will go over it on the next and last slide. Alrighty, so we have 5 orbitals here, and we can probably assign them based on what we know. Hopefully remember that an orbital gets larger the higher the energy level. The diameter of it gets larger. So we have 2 different size p orbitals. So the smaller one would be the 2p, and the larger one would be the 3p. The clover shape is a d orbital. We only have one of those, so 3d. Actually, the d sublevel doesn't start until you get to the 3rd energy level. We have 2 s orbitals. The larger one would be 3s, the smaller one would be 2s. So that takes care of assigning these designations to the orbitals, but it's not really fully answering the question, which is asking you to assign quantum numbers. Yeah, I changed it and made it harder. Assign quantum numbers. So the quantum numbers for the 2p, so would be 2p would be n equals 2, the 2nd energy level. And what is the L value for a p orbital? It's 1. So those would be the first 2 quantum numbers for 2p. Let's do the same for 3p. N equals 3. L value for p sublevel is 1. 3d, again, n equals 3. See, n is the easy part. L for a d orbital is 2. The 3s, n equals 3. L is 0 for an s orbital. And the 2s, n equals 2, and L equals 0 again. So you can assign the first 2 quantum numbers based on the energy level and the shape of the orbital. We cannot do the orientations and space and spin until we start putting electrons in them. All right, the second question asked you, which orbital could have the quantum numbers, potentially, of n equals 3, L equals 2, and m sub L equals 1. So, let's see, if the primary energy level is 3, we can cross out anything with an energy level other than 3. All right. L equals 2. That means, let's see, 0 is S, 1 is P, 2 is D. So L equals 2 means it's a D orbital. I think that's the same question I just asked. Oh, well. Yeah, so let me, it is the same question I just asked. But oh well, I'm not going to change it now. So let's talk about m sub L equal 1. What are the values that m sub L could have if L equals 2, like it does here? Okay, m sub L varies from minus L up through 0 to positive L. So the values m sub L could have would be minus 2, minus 1, 0, plus 1, and plus 2. So m sub L could have 5 values, and that's because the d orbital, d sublevel, has 5 orbitals. So the m sub L values correspond to how many orbitals are within a certain sublevel. That's it for this bizarre concept. And so the next lecture will be Chapter 8, and it will be electron configuration.